Hello and welcome, class. Happy Friday. Welcome to another lecture. We have just finished talking about all of the essentials for equilibrium in chapter 15, so now we are going to move into the tail end of chapter 17. This move may seem strange, but the reason why I am taking this approach is I want to mirror the same topics that we talked in chapter 9 kind of in the same order. So we're going to do solubility first and connect this to equilibrium. We're going to do acids, bases, and then we're going to do redox. It just so happens, though, that in the chapters to come, the lessons to come, solubility is in the second half of chapter 17. Acids and bases cover the entirety of chapter 16 and the beginning of 17, and then redox chemistry is 18. So it may seem like out of place to just be jumping into the tail end of chapter 17, but this is why I am doing it. The conversation of solubility does not hinge on having already talked about acid-base chemistry. It only depends on us having talked about equilibrium. So that's why we're going to do this. Let's talk about solubility, specifically of those mostly insoluble compounds that we've kind of left off or left in the gray area from last semester. So if you don't remember from last semester, or if you were not with us last semester, we covered a series of solubility rules. Solubility rules. I've posted those rules again on Blackboard if you want to review them, but they lay out the hypotheses behind what types of ionic compounds are going to be soluble when. So is iron nitrate going to be soluble? Is silver chloride going to be soluble? And there were some compounds that were listed just as like mostly soluble or mostly insoluble. And I left that kind of patch of gray in the dark. What we're going to do now is illuminate this concept of mostly insoluble versus mostly soluble, all under the umbrella of equilibrium, and how can reversible reactions help us to actually understand what's happening in these mostly insoluble compounds. Okay, so let's talk a little bit about solubility. We're going to shine a new light on solubility as well, a little bit more technical. Our conversation of solubility last semester primarily had to do with the qualitative description of solutes existing inside of solvents, and we did talk about the nature of solubility this semester, that with an increase in temperature, generally we see an increase in solubility of the solute particles hanging out inside of your solution. So the concept of solubility and how it connects explicitly to the definition of a saturated solution. We can measure the solubility quantifiably of a solution, and this is the maximum amount of your solute that can dissolve in a given quantity of solvent at a specific temperature. Now, this is going to be measured in grams per liter. So in other words, once we have a saturated solution, we have as much solute as we can fit. The spheres of hydration cannot accommodate any more solute going into the solution. We're going to have a certain mass of stuff inside of this given volume of solvent. And so the solubility of a saturated solution we can actually measure, because one more particle of solute being added into this container would just sink to the bottom. There's no way for water to accommodate it. It's not going to form a solution. It's going to remain separate, this little heterogeneous piece of leftover solute at the bottom. So the amount of stuff that's in solution defines our solubility. Now we can also rewrite our solubility known as our molar solubility with the shorthand of this lowercase s, this variable s. This is the number of moles dissolved in 1 liter of a saturated solution. So notice that solubility, the molar solubility, is defined similarly to the same type of concentration, molarity before. So we have moles of a solute in some volume, specifically that's in liters of a saturated solution. So we're still looking at liters of solution here. Okay, so we can use the molar mass, grams per mole, to convert between the two of these. So the solubility in grams per liter can be interchanged with the molar solubility that is in moles per liter, here using grams per mole. Okay, so let's tie in then those mostly insoluble compounds. Solubility rules, again, that I've posted on Blackboard as a refresher, can be used to determine whether an ionic compound is mostly soluble or mostly insoluble. But what does that really mean? We're going to be focusing on the mostly insoluble, but the same types of arguments can be made for mostly soluble compounds, and we'll talk about that a little bit later. The mostly insoluble ionic compounds, when the solid itself is placed in solution, we can say are going to slightly and reversibly dissolve in aqueous solution. In other words, these types of compounds like this lead iodide, which we would predict using our solubility rules to be a mostly insoluble compound, so this is an example of a mostly insoluble compound, we would predict this to just sit in solution. It would be mostly insoluble. But mostly insoluble, meaning that most of the time these ions are recombining to form a solid. Some of the time, though, we have a little bit of dissociation, right? So these forward and reverse reaction arrows, tying them back to the idea of rates from before. Here we would have a very fast rate going backwards, very high reaction rate going from the ions into this solid, but a very tiny, right, little tiny reaction rate going from the solid into the ions. This reaction will eventually hit some type of equilibrium, giving us an equilibrium constant that we can write out. So in fact, let's do that. What is the equilibrium expression for a mostly insoluble ionic compound? Since this way of writing the formula is going to be the common thread. This is the, by convention, standard way that we write a mostly insoluble solid partially dissolving into ions in solution. So we're, again, going to be writing our equilibrium expression as an expression of products over reactants. This does not change, right? Just because we have slightly altered the focus of our equilibrium study doesn't mean that we throw everything out the window. We are still going to be writing a ratio of product concentration divided by reactant concentration. It just so happens in this case that the mostly insoluble kind of like concept that we're working with, we are working with heterogeneous equilibria, right? We have aqueous species on the right-hand side and solid on the left-hand side. And when it comes to the heterogeneous equilibrium expressions, as a reminder, we do not include solid or liquid in our equilibrium expressions. What this means is that the equilibrium expression is only going to be equal to the concentration of our lead 2+ ion times the concentration of our iodide ion, and because we have a coefficient of 2 in front of the iodide, we're going to square it. So this is going to be what the equilibrium expression looks like for a mostly insoluble compound. It's almost always, like 99 times out of 100, going to be equal to the concentration of the ions that are the product of the dissolution, and the solid itself, it doesn't matter. And again, we don't include the solids or the liquids, but in this section we're going to be seeing solids mostly. The reason we don't include those solids is specifically because, again, the densities don't change. So even if we included something like density of lead iodide down here, across the board with all of our different calculations, different temperatures, etc., this density doesn't change. And so if it doesn't change, it's not going to alter this measurement of K or the idea of these concentrations in any way. So if it's just a constant, we might as well drop it. If we're looking at ratios, it doesn't give us any additional information. So we're just going to be focusing on the aqueous components here. Okay, so what does the magnitude then of this equilibrium expression mean? Well, before talking about that, let's introduce then the new notation for this specific type of Kc. And this is, the C now we can see is going to be changed in this context to an SP. We call this our solubility product. This is the equilibrium constant expressing the product of solubility. So in other words, the Kc that we just found on the previous slide, if we are working with mostly insoluble species, we are going to rewrite this K as a KSP. There's no like conversion that we have to do. It's just a simple label change. We are changing the subscript to an SP to specify that we are working with some type of heterogeneous, mostly insoluble type of equilibria. So we see two additional examples of this type of solubility equilibria below. We have strontium sulfate, which we would predict to be mostly insoluble. Now this bismuth sulfide was not necessarily on the list. I mean, sulfides were, we could assume that this is mostly insoluble, but just because both of these compounds we would label before as mostly insoluble doesn't mean that they are mostly insoluble to the same degree. In fact, the strontium sulfate, which breaks into our strontium and our sulfate, we see has a KSP that is equal to 3.8 times 10 to the negative 7. We're going to look at these magnitudes for comparison's sake. The bismuth sulfide, which breaks into bismuth and sulfide, as one would expect, has a KSP that is 1.6 times 10 to the negative 72. This is a huge magnitude difference. And what this really means is that, again, if we're looking at these KSPs being a measure of like product over reactant, where yes, the reactant we're not explicitly going to list, but we're still going to look at this KSP conceptually as this like meaning of product to ratio or product to reactant ratio. The first KSP for strontium sulfate is bigger. What this means is that we have more product, right? A larger KSP means more relative product. And in this case, the product that we're looking at in both cases are ions that have been dissolved in solution. So a larger KSP is also going to mean that your quote unquote mostly insoluble solid is more soluble. We can dissolve more strontium sulfate in water than what we can bismuth sulfide. In fact, this magnitude, this negative 72, or the 1.6 times 10 to the negative 72, is so incredibly small, we would have like one ion in solution. Like one of the molecules would break apart, but we would have this very heavy reverse equilibrium balance where most of the bismuth sulfide is just going to remain as solid. And that's not to say that 10 to the negative 7 isn't also a small number, relatively speaking to other numbers that we've been looking at for equilibrium constants, but this is to say that it is a larger KSP, meaning that more of the strontium sulfate will be able to dissolve. Okay, so where can we find tables of these KSP values? Since the solids that we're looking at are mostly insoluble solids, this is not, an indefinite list of solids that we could be looking at. So we actually have a couple of places where we can go find already like predetermined KSP values. So in table 17.4 in the text, as well as appendix 3, we have a bunch of solubilities. That's actually where I grabbed these two solubilities from. So if you are working on homework problems and a KSP is not given to you, feel free, to check out these tables here and pick out the KSP that you are going to presumably be working with. All right, so what does solubility quantifiably mean then? If we're working with an equilibrium constant, and I just said that some things are more soluble than other things, well, surely then we can calculate how much stuff is actually in solution. And this is exactly what we're going to demonstrate here. We can calculate the solubility S, so this is again our molar solubility, S, that we're first going to be finding for magnesium carbonate. This is another substance that we would predict to be mostly insoluble. KSP is provided here, a 6.8 times 10 to the negative 6. So this is on the same magnitude as the strontium sulfate that we just looked at. Now this is a component inside of the mineral dolomite. Let's also then, once we have the molar solubility, just for the sake of practice, find the basic solubility in grams per liter. Let's see if we can't find the value in both of these units. Okay, so the way that we set up this problem is the exact same way that we have been setting up any type of equilibrium constants type of problem. So we're going to set up first our reversible reaction, the magnesium carbonate, which is a solid. This is going to dissolve reversibly in water, giving us magnesium 2+ and CO3 2-. Both of these will be aqueous. All right, once we have the dissolution written out, it's just a matter of entering data that we either have or don't have in some type of ice table. And this may seem a little strange since we're not given any information aside from the KSP of the magnesium carbonate, but here's sort of the implied direction that we're going to be starting from. First, Our magnesium carbonate, again, since this is a solid and this species does not get included in our equilibrium constant, we're not going to fill out any information here. It doesn't matter. It doesn't matter how much we start with. If we add too much or too little, the question is, what is the solubility? How much solute would theoretically be able to fit inside of a given volume of solvent? So it doesn't matter how much we're starting with, we're looking at a hypothetical theoretical limit. What is the amount we could add to a saturated solution? All right, well, you might then ask, how can we find that if it doesn't even matter how much magnesium carbonate we're starting with? Well, here's how we can find it. The KSP tells us the threshold limit, how much stuff can fit inside of solution when our stuff is magnesium carbonate. So if we throw in some amount of magnesium carbonate, doesn't matter how much, initially, we would assume that we're starting, right, with just pure water. We're taking magnesium carbonate and we're throwing it into some container that is just pure water. And if this is our initial condition, we're taking some stuff and throwing it in pure water, well, that means that we don't have any magnesium or carbonate to start with. Now, in order for this reaction from these initial conditions to change and reach equilibrium, there's going to have to be some type of shift from the magnesium carbonate as it partially dissolves into the magnesium and carbonate ions. This shift we're going to represent with an S. Now, don't be thrown off by S's being listed here instead of X's. I just want to be consistent with the textbook in this regard because I don't want suddenly a new variable to show up and for people to get confused. This S functions in the exact same way as X that we were using before. It's just a variable to represent some type of change as equilibrium is being reached. So from here we have the magnesium carbonate dissolving into some amount of magnesium and carbonate being represented by this S. And so once we've reached equilibrium, the amount that we're going to have is going to exactly be equal to S. So now we have one unknown and one equation that we can set up using this KSP. All right, so I've erased some of the writing from over here. Do not be alarmed. Quick cut, just erase that material so I have room to work and write out what that KSP expression is going to be equal to. So again, products divided by reactants, but it's only the product that is going to matter here since these species are in aqueous form. The KSP is going to be equal to the concentration of our magnesium 2+ times the concentration of our CO3 2-. No exponents necessary since there are no stoichiometric coefficients here, so it's just a matter now of inserting what our KSP is equal to, the 6.8 times 10 to the negative 6, and this is going to be equal to S, which is the concentration of our magnesium, and S, the concentration of our carbonate. Well, this is just equal to S squared. And the easiest way to solve for a square is to take the square root. And so this is going to give us what our S is equal to, at least in the units of moles per liter. Again, this table here, all of the variables within it, in order to work with KSP, are going to be in mole per liter units. Has to be. So it doesn't matter that our KSP does not carry any units explicitly with it, so long as we remember that this KSP is a molar equilibrium, then we will remember that the S's that we calculate on the other end, which in this case the square root of 6.8 times 10 to the negative 6 is a 0.0026, the units will be molar. All right, so here's the first value that we were asked to find. The molar solubility S is going to be some type of mole per liter unit. Now let's find what this value is in grams per liter. The easiest conversion that we have to do is just take this, multiply it by our molar mass. So the 0.0026 mole per liter, we're going to take this and multiply it by the molar mass of magnesium carbonate, which is an 84.31 grams per mole. So here now we can see our units of moles are going to cancel, and this will leave us in a unit that is grams per liter. And our grams per liter are going to be a 0.22 measure for solubility. All right, so what all of this means is that we can take either 0.0026 moles of magnesium carbonate, or in a more conceptual measurement for us, a more direct measurement, 0.22 grams per liter or grams of magnesium carbonate, and this would dissolve in 1 liter of solvent. We would have no precipitate. It would be completely dissolved. We would have a saturated solution. Any more than that 0.22 grams would just sit at the bottom of our beaker, sort of like sand or glass or any type of solid that we would put in a flask of water that does not dissolve. It would just sit there. Okay, so let's talk about how the idea of solubility then connects to precipitation reactions. Now, we did this last semester as well. We predicted based on some type of cation plus some type of anion, if they combined together to make Ca, was Ca soluble? We would look at this compound, try to find it somewhere on, the solubility rule list, and we would determine, is it mostly soluble or mostly insoluble? Well, here we can do the same thing quantifiably. So we don't have to have a bunch of rules memorized for a bunch of different compounds. If we know what our KSP is, and we know what our initial conditions are, this Q is the exact same reaction quotient from chapter 15. So if we know our initial conditions and we can compare them to equilibrium conditions, we can, predict whether or not a precipitate is actually going to form. So if we take some type of cation like lead, mix it with iodine to create lead iodide. Now this is the compound that we're going to say, okay, if it is mostly insoluble or not, it in solution will start as some type of solid and will then react reversibly to dissolve. Now we can set this up whether or not we know our compound is going to be mostly soluble or insoluble. The process is going to look the exact same. We have a Kc given here. Now if our initial conditions compared to this K, so we know how much stuff, how many of our lead and iodide molecules that we're putting into solution because we have some type of concentration measured. Again, if we write the reaction in the forwards or reverse direction, it doesn't matter, just so long as we are looking at the problem consistently. And so this is going to be the consistent perspective that we are going to take, since we have an equilibrium constant here that we can actually compare initial conditions to. If we know the initial concentration of our lead and our iodide, we can compare the initial conditions to Kc by taking the initial conditions, Q, and inserting them to find a reaction quotient. Right, so here's our Pb2 plus initially, and our iodide squared initially. So if this calculation for Q, when compared to K, Q is less than K, well, what this means is that in order for Q to be smaller than K, if we're looking at this versus this, let's compare the right-hand side since this is where useful information is. What this means is that the value of our lead concentration and iodide concentration, our products, in other words, are too small, right? We have too little of our product compared to our equilibrium conditions. Well, what this means, if our products are too small, it means that we don't have enough ions. Not enough ions. We have not made a saturated solution yet. What this tells us, if we have not made a saturated solution, is that more ions can still fit inside of solution. In other words, if our Q is less than our K, no precipitate will form. Right? And no precipitate will form because we don't have enough ions in solution yet. We have not reached a saturation point. Now, if Q is greater than K, this is going to mean the exact opposite. If Q is too big, that means that our initial conditions, there are too many ions. Our products are too big. Mathematically speaking, we have too much stuff in solution. Too much stuff. There are too many ions. Not everything can fit. So if your Q is greater than K, if your reaction quotient is greater than your equilibrium constant, then a precipitate will form. The reaction will have to shift away from the products, and if it does that, it's going to shift towards the reactant, which in this case is a solid lead iodide, meaning that we would see some type of precipitate form. So let's look at some hypothetical numbers then. Let's actually plug some numbers into the equilibrium reaction, reversible reaction. My brain just farted there. A reversible reaction of our lead iodide, solid, not gas, dissolving reversibly with lead 2+ in aqueous condition, and our 2 iodides aqueous condition. So we just saw, and as we have also written already, our Kc, which is going to be equal to the concentration of our lead 2+ times our iodine concentration squared. Now in the wording of this problem that I have yet to read out loud, we can see is equal to numerically a 1.4 times 10 to the negative 8. So this is going to be the value that we are going to compare our Q to. Now what we are mixing together is a 4.3 times 10 to the negative 3rd molar solution of lead nitrate. So this is going to give us our lead concentration here. And it is mixed with a 7.8 times 10 to the negative 4 molar solution of sodium iodide. This is going to give us our iodine concentration here. The question is, will a precipitate form? All right, so how we can solve this problem is set up our Q, and we're going to compare our Q to our K that is now listed to the left. Our Kc, again, which is some type of solubility product. We could also write this as a KSP. It doesn't matter. Both of them are the same variable. There's no mathematic calculation we need to do to interchange between the two. It's just a simple label change. So the Q is going to be equal to our concentration of lead 2+ times the concentration of our iodine squared. So we're going to take the concentration of our lead, which is given to us up above, a 4.3 times 10 to the negative 3rd molar. The concentration of our iodine is 7.8 times 10 to the negative 4 molar, and we're going to square that value. And this is going to give us a reaction quotient that gives us information about the initial conditions relative to our equilibrium expression and our equilibrium constant. So the calculation of 4.3 times 10 to the negative 3rd and 7.8 times 10 to the negative 4 squared gives us a 2.62 times 10 to the negative 9. Now this reaction quotient Q is going to tell us whether or not we're going to get some type of precipitate, and we're going to compare this Q to our K here. So our question is Q less than K or is Q greater than K? Now in this case we can see that a 2.62 times 10 to the negative 9, this is one full magnitude smaller than our K. Our Q is less than our K. And since our Q, our reaction quotient, is smaller than our K, what this means is that we don't have enough ions in solution to have reached a saturation point. We are going to need more ions to reach saturation. Given the concentrations that we have mixed together, we would not see a precipitate form. There's not enough lead and iodine in solution to cause the reaction to shift to the left to create any type of lead iodide. There would be no solid. We would see two solutions that are clear and colorless being mixed together that would also result in a clear and colorless solution. Now this may seem counterintuitive. Again, based on our solubility rules, we predict that if lead and iodide get mixed together, we would see some type of precipitate form because lead iodide is a mostly insoluble compound. However, what we're doing now is that we're actually looking at, again, the gray area. What happens when you don't have enough ions in solution to actually cause some type of solid to form? This is exactly what's going to happen. The calculation that we've just done demonstrates or links together the idea of solubility in saturated solutions with equilibrium. And now we have a means to predict every time, not just based on general rules, but every time whether or not we will see some type of precipitate form. Okay, so notice that we didn't have to do any complicated ice table here. We didn't have to find any type of equilibrium calculation or concentration. Didn't have to go that far. if we're looking at whether or not a precipitate forms, all it is a simple measure of Q versus K. So if you can find your Q and you already have a K, or vice versa, if you have a Q but you're trying to find a K but you have equilibrium concentrations, or you can look it up in the tables provided, you have a way to figure out whether or not a precipitate will form without any additional calculation. Okay, so the last thing that we're going to do, there's one more type of like quantitative thing we're going to talk about, and then we're going to shift into just qualitative to like wind down for the rest of the lecture. So let's tie Le Chatelier in with this concept of solubility, because if we have some type of solid that's reacting reversibly to make some hypothetical cation and anion, well, surely then, since this is a reversible reaction, Le Chatelier's principle is going to apply. So if we create some type of stress and apply that to the reaction, we're going to be able to shift it either to the right or to the left. And we can predict the shift in the exact same way that we did in chapter 15 when we looked at Le Chatelier's principle. So solubility of these mostly insoluble compounds are going to be affected by a number of factors, and these are the four that we're going to focus on. The common ion effect, which is a new term that we're going to introduce in a couple of seconds. We have temperature dependence, just like before. In chapter 15, temperature, we said when we were taking a closer look, didn't just shift the equilibrium, but it actually changed the value of K itself. So the same concept is going to happen here, since the dissolutions of these types of solids are going to be exothermic or endothermic. Most of the time they're endothermic. We would be able to predict some type of temperature response to solubility of these reversible reactions. Acidity and alkalinity, as long as you know what an acid and a base is, that's the total amount of information that we need to be able to have this conversation. So we're not going to be tying in any type of like weak acid base pH type of calculation here. It's just a simple, if you add acid or base, you can predict a shift in the reaction's solubility. Last but not least, complex ion formation. So we already know what a complex ion is. We've talked about this in lab a couple of times. These are the types of ions that are not just simple form, but they're polyatomic ions, normally containing some type of metal in the center. They're surrounded by some number of what we call ligand. In this case, I'm just drawing a bunch of ammonias, NH3s, surrounding this copper, and the total complex, where each of these bonds is not a covalent bond, it is some type of non-covalent or dative bond. It's an intermolecular force holding each of the ammonias to the copper, and this whole thing is going to have a polyatomic ion charge of +2. So this is what we mean by a complex ion. And complex ions can form in solution, and that's going to also affect the solubility of your mostly insoluble compounds. Okay, so let's talk about how each of these then variables in turn affects solubility, starting with the common ion effect. Okay, so what the common ion effect is, first we have to break down what is a common ion before we can talk about the effect it has on your solution. So a common ion is this first definition. It is a solution that is already going to contain some type of solute ion that is in common with your reversible reaction. In other words, if we wanted to add magnesium carbonate into a solution, not a pure water bath, but a solution of magnesium 2+. Let's say there's just a bunch of magnesium 2+ already floating around in the solution, and we add magnesium chloride to it. The magnesium 2+ that's already present in solution is going to be the common ion. Since when magnesium carbonate breaks up, one of the species it breaks into is magnesium 2+. Here we can see the magnesium 2+, which is already present, is an ion that the two pieces have in common. One piece being the solid that you're going to add into solution, your magnesium carbonate. The other piece is the ion that's already in solution. All right, so the effect that this common ion is going to have is that it decreases the solubility of your mostly insoluble compound. Now, we would be able to predict this already according to Le Chatelier's principle, right? If you increase the concentration of one of your species, if you increase the concentration of your magnesium component, your magnesium ion in this case, we would predict that we are going to get a shift away from the ideal equilibrium because we've increased the concentration of one of our products artificially. And so what we're going to do, again, here's our little Hot Wheels car. This car is going to represent the shift in the reaction according to Le Chatelier's principle. If we increase the magnesium 2+ concentration, we predict that this reaction is going to shift back towards the magnesium carbonate in order to reaccommodate and reach equilibrium. Now, this exactly demonstrates what we just said. A common ion, in this case the magnesium 2+, is going to decrease the solubility, and the solubility decreases because the reaction shifts back towards creating more of this insoluble solid. Okay, so if we want to, though, put some quantifiable calculation to this, can we do that? Can we predict, well, what is the new solubility if we already have some magnesium present? And the answer there is, of course we can. We can always quantify. The question is, do we want to? And here the answer is yes. So before, the solubility that we found for magnesium carbonate was a 0.22 grams per liter, right? That was like 2 or so examples ago. So what we're going to do now is take the same magnesium carbonate and we're going to add it to a 1 molar solution of carbonate, right? We just have carbonate solution, like soda or baking soda. Let's say we just added a bunch of like sodium carbonate. Sodium doesn't matter. The carbonate is the common ion. So what is the new solubility of the magnesium carbonate in solution in grams per liter? Right, so before, the magnesium carbonate in just pure water, its solubility was 0.22 grams per liter. So we're going to kind of keep this in the back of our mind. How we set up this calculation, we are going to be using the ice table type of format again. So let's set up our reversible reaction. The magnesium carbonate, which is a solid, is going to dissociate and create magnesium 2+ in aqueous solution, and the carbonate 2- also in aqueous solution. So the major difference here when setting up our ice table, because before we didn't have any magnesium or carbonate initially, we just put 2 zeros here with our initial conditions. The only real difference is that now we have some type of additional piece. We have 1 molar solution of carbonate initially. So this 1 molar solution of carbonate is going to have to go right here in the initial condition under carbonate. Now we don't have any magnesium. That part is still consistent. We don't have any common ion of magnesium here, but we do know that since there is a 0 here, we are going to get some type of shift from reactant to product in order to create some magnesium. And again, the amount of the magnesium carbonate specifically doesn't matter. Since we're working with a solid, we're just going to put dashes all the way down the line. We don't have to worry about what this reactant concentration is, since there's no concentration of solid that we can actually measure as a variable. So the shift that we're going to get is going to be from left to right. The change that we're going to predict is that we're going to create at least some magnesium here. We're also going to get a +S here, since both of these are on the product side. We're going to get a shift from reactant to product, creating a little bit of both of these. So the equilibrium concentration of our magnesium is going to be an S, and the magnesium carbonate concentration at equilibrium is going to be a 1 + S. Okay, so here now we have a way to calculate what the S is going to be using our equilibrium expression, right? Our solubility product for this species, which was given before, is a 6.8 times 10 to the -6. This value is still the same. The 6.8 times 10 to the -6 value is going to be equal to, again, our concentration of magnesium 2+ times our concentration of CO3 2-. This does not change. What does change are the variables that we're going to be plugging in for the magnesium and the carbonate. The magnesium is a value of S. We don't know what this unknown change is. That's going to be exactly what we're solving for. The concentration of our carbonate is a 1 + S. So here we now have a setup, an expression where we have one equation and one unknown. This is our S. So let's distribute our S into the parentheses here. We have an S + S squared. And all of this is going to be equal to the equilibrium constant value, this equilibrium constant of 6.8 times 10 to the negative 6. So we're going to subtract this to the other side. We're going to subtract it because currently it's sitting right here. We're going to subtract it over 6.8, subtract it, times 10 to the negative 6. And this gives us a way to use the quadratic formula to solve for what our S is going to be equal to. Now, I'm not going to show all of that work. I leave that algebraically as practice for you. But when going through the quadratic formula and solving for our new S, given these conditions, what our solubility is in molar units, again, because first we find molar units, is going to be equal to 6.8 times 10 to the negative 6 moles per liter. We see such a small shift, a small solubility when compared to the original case, because we have this extra one here. We're starting with some product already. Now, if we convert this using our molar mass, so we have a solubility we can actually compare to the one on the right that is in the grams per liter, we're going to multiply this by 84.31 grams per every 1 mole, since this is the molar mass of the magnesium carbonate. And this is going to be equal to 5.73 times 10 to the negative 4 grams per every liter. Right, so again, this S, I did not explicitly show the math for solving for this 6.8 times 10 to the negative 6 value, but you can use the quadratic formula as we did in chapter 15 to solve for this. Okay, so the value here of the 5.73 times 10 to the negative 4, we can see is definitely less than the value from before when we just added magnesium carbonate into pure water. So this represents the common ion effect, that if you're adding a solid into a solution that already contains some of the product ion, you're going to see less of a dissolution, less of a shift of the magnesium carbonate into the products, since we already have so much of one of the products there. Okay, so just like before, temperature is going to affect your equilibrium expression. Now I'm just going to be focusing on this qualitatively. We've already talked about the quantitative association of temperature and K and all of those values. So what I'm going to do right now is just focus on the heat being as either a reactant or product, depending on if you're working with an exothermic or an endothermic dissolution. Now most dissolutions are endothermic. Most require heat as a reactant in order to break up your compound. The endothermic nature of the reaction then is going to cause temperature to play an effect in the equilibrium balance of the reaction. So let's look at this dissolution below. Potassium nitrate as a solid with a little bit of heat is going to break down into potassium and nitrate ions. This reaction is actually a reaction that we worked with back, it was like lab 11, maybe it was 12, question mark. Where we were measuring the thermodynamic nature of a bunch of stuff, measuring the, in this case, it was the enthalpy of solution, and we found that the enthalpy of solution was positive, meaning that we were working with an endothermic reaction. This dissolution of potassium nitrate requires heat. This is also a compound that, according to our solubility rules, is mostly soluble. However, I want to point out that this compound does have a measured solubility. The solubility is 500 grams in a liter of water. And this is at a temperature, greater than room temp. It's around 33 degrees Celsius, not too much higher than room temp, but it is a reasonably high solubility, especially compared to the solubilities that we've just been looking at, right? This is anywhere from 1,000 to 1,000,000 times larger than the solubilities of the insoluble compounds. So that's just to show the range of solubility that we can have here. If a compound is mostly insoluble, we can put a lot of it into any given volume of water. However, this reaction is, again, endothermic. So we would predict that if you were to, let's say, decrease the temperature, what's going to happen is that the reaction, as it is written here with this reversible reaction arrow, is going to shift from the products back towards the reactant. In other words, if you decrease the temperature, you are decreasing the amount of ion that you can actually put into solution, forcing more and more of the potassium nitrate to remain as a solid. Even though this is a mostly soluble compound, if we were to decrease the temperature enough, we could turn it into a mostly insoluble compound. Right, there is a temperature dependence for this reaction because it is endothermic. And if we were to decrease the temperature so much, this solubility would decrease effectively to a point where it's going to behave as a mostly insoluble compound. Now, if we wanted to look at the flip side of this, let's say the lead iodide, which, as we've been seeing, reacts reversibly to create some lead 2+ and iodine minus in aqueous conditions, where this is our solid, these are aqueous. This reaction is also, plus heat, endothermic. So we would predict that if we want to increase the solubility of this compound, we would just jack the heat up. If we turn the temperature up, this reaction is going to shift more towards product. We would be able to fit more of the ions in solution. We would turn its solubility up. And in fact, if we increase the temperature of a lead iodide solution to about, like 70, 80 degrees Celsius, we can actually get an appreciable amount of the lead iodide to dissolve and turn it into a clear colorless solution and remove all of the solid. In fact, there is a demo video that I have linked in the Chapter 17 Part 1 folder that demonstrates a reaction that, when performed, is known as the golden rain. This is a very famous demo. I would have loved to have been able to do it for you guys in person, but I feel like the video that I have linked does a better job at recording and presenting it than what I could have done. So I am going to share that video with you guys. Definitely give it a look-see, but it tells or demonstrates not just how we can create precipitates from the ions combining, forming saturated solutions, crashing out and giving us a precipitate, but also how the temperature plays a huge role in how the solids form. All right, so acidity and alkalinity. Again, we're just looking at how acids and bases play with these types of reversible reactions. Okay, so we have a reaction given below. We have iron oxide, which is a mostly insoluble solid, reacting reversibly to dissolve and give us some iron 3+ and 3 hydroxides. This is a really good example of how an acid and a base can interact with this reaction, since we have hydroxide right here. This is going to be a very straightforward example. So let's say we want to increase the alkalinity of your reaction. We want to increase the alkalinity of the solution. Well, alkalinity is just a fancy word for basicity. It is pertaining to the base component, not the acid. So the alkalinity of the reaction we can increase if we increase the concentration of our hydroxide. So if we add some more hydroxide or add some more base into the solution, well, we can get a prediction that if we're increasing this concentration, we are increasing that side of the track. Thereby, we would predict increasing the amount of solid that we would have in solution, right? The reaction would shift from product to reactant if we added more base into this reaction. Okay, I'm going to switch colors here for this next part. The acid then is also going to have an effect. The acid is going to have an effect because an acid is able to combine with this base. If we add acid into a reaction where OH is present, this will result in a neutralization reaction. Now, this reaction we've talked about back in Chapter 9. This shouldn't be anything new. If we add H+ and OH-, we end up with HOH, which is exactly water. Now, if we add H+ to the solution, what we're actually doing is decreasing the concentration of the OH that is available in solution, since we're neutralizing it and turning it into water. This we would expect then to have a similar effect on the equilibrium, where before we had some nice equilibrium threshold. If we've decreased the concentration of our OH-, our car then is going to exactly shift in the opposite direction as before. We're going to be shifting from the reactant to the product. So in this particular equilibrium reaction, if we were to add acid to it, we would expect to see more and more of the solid dissolving and turning into this iron oxide dissolved solution. So if there are similar reactions set up with OH minus, H plus being available somewhere in the reaction, changing the acid and base nature, increasing acidity, increasing basicity, or decreasing acidity, decreasing basicity, we would expect to see some type of shift in the equilibrium as a result. And that's specifically, at least in this case, because we see hydroxide is present in the solution. Okay, and the last factor that we're going to talk about, tying Le Chatelier's principle into the solubility product, mostly insoluble type of equilibrium chemistry, is the formation of complex ions. Now, complex ion, again, is that kind of complex polyatomic ion where we have some sort of metallic center to it. So a complex ion being present in solution is known to increase your solubility. So unlike the temperature and the acidity-basicity component, where you can have an increase or a decrease, all depending on what the context of your reaction is, here, complex ion formation is always going to increase the solubility of your solid. So let's look at the reaction below to kind of demonstrate why that is. So your solid here, copper hydroxide, is a solid, also insoluble, is able to react reversibly to create some copper 2+ and some hydroxide with a single minus charge in solution. So let's say we want to add some ammonia to this solution. Well, ammonia is known to really bond well through intermolecular forces with copper. In fact, if we were to add 4 of these ammonia into solutions, let's just make this a very clear 4. We're adding 4 ammonias to solution. These 4 ammonias are known to surround themselves around copper very readily. What this does is creates another reversible reaction that is present in solution. So this copper plus the 4 ammonias is known to be able to give us the complex ion that I have listed here. So we have a copper, and these brackets are not concentration of, this is just like an outer set of parentheses. So in fact, just for clarity's sake, I'll just make these another set of parentheses here. So we're not looking at specifically a concentration of, but here we are looking at a polyatomic ion where we have a copper in the center surrounded by 4 ammonia. There's a 2+ charge on it. This reaction, creating the complex ion, is also reversible in solution. It is not going to be a straightforward like precipitation reaction. Because the ammonias are only held on the copper by intermolecular forces, if we increase the temperature enough or increase the energy in solution enough through like stirring, we can knock a couple of the ammonias off. So this is definitely a reversible reaction situation. But if we add ammonia in the first place, we are going to be decreasing the copper concentration in the first reaction. What this means is that we are going to have to shift from reactant to product to accommodate the loss of the copper. We're going to have to create more product in order to replace the copper that is lost when forming this complex ion with ammonia. So here's how we can see that the complex ion formation from a metal ion that is dissolved in solution is always going to increase the solubility of the solid that you started with. Because when we make a complex ion, we're always going to be pulling some of the ion away from the original dissolution reaction. Now, what's really cool about this type of problem, this type of equilibrium, because we have 2 reversible reactions linked together inherently, now we can also change or shift the nature of our first reaction by shifting something according to Le Chatelier's principle in the second reaction. So adding stress to either one of these reactions now is going to inherently affect the other. We're not going to work through any of those types of problems quantitatively, but suffice to say that since we have another equilibrium expression here, we can write another type of equilibrium constant for this expression. Now, this type of equilibrium constant, just like how the solubility of our mostly insoluble stuff has a special equilibrium constant known as KSP, the formation of a complex ion also has a special equilibrium constant known as KF, K of formation. Now, for this type of expression, we're going to write out, or for this type of reversible reaction, we're going to write out the expression in the exact same way, again, that we have before. It's always product divided by reactant. And in this case, all of our products and reactants are aqueous. So the equilibrium expression here would be concentration of the CuNH3 4 2 plus, all divided by the concentration of our copper ion, Cu2 plus, and the concentration of our ammonia, and that's going to be raised to the fourth since we have a 4 in front of the ammonia. Now, are we going to be doing anything quantitatively with this Kf? Probably not, but I still wanted to introduce the concept of the Kf just because it is also laid out in the textbook. I don't want there to be any type of confusion because I haven't addressed something that's in the textbook for anyone who is like adamantly reading along at this point because we are all at long distance. But if we were to work through some type of Kf problem, it would not be in this larger context tying these two reversible reactions together. That math just gets really messy really fast. So when it, moving forward, when it comes to these types of problems, we're always only ever going to be looking at one equilibrium context at a time when we're actually quantitatively working through the problems. Qualitatively, we can stack together as many reversible reactions as we want and use Le Chatelier's principle to predict the direction of the reactions if we add a stress to one, which will have an effect on another, which will have an effect on another. That's pretty easy to predict. Quantitative stuff gets very messy. So this is going to be where we then conclude our conversation on solubility for now. But we do have a way then now looking back to, without having to memorize any certain set of rules, we have a way to predict whether or not a solid is going to dissolve in solution, whether a precipitate will form if we've mixed two solutions together. We know exactly how much of that solid is going to dissolve into solution, like what the solubility actually is. And we also have the means to predict, based on changing other factors, other stressors, how the solubility of that solid is going to be affected. So with that, here I have a couple of example problems for you. So solubility equilibria is going to be like calculating the solubility, calculating that S without any additional factors present, and then factors affecting solubility. These are going to be more of the common ion effect type of problems, as well as the basic Le Chatelier. But quantitatively, we're going to have some common ion effect problems in here. Up above, just some simple solubility solving for S types of problems. All right, so if you have any questions on solubility, how it connects to the equilibrium concepts that we've talked about in chapter 15, definitely give me a shout out either via email or on Discord. But with that, no additional announcements other than, I am going to be posting this on Blackboard as well, so you might see it there before you hear the announcement here. But originally we had an exam scheduled for next week. We are going to be bumping that exam back by 1 week. Yes, our exam 3 we held basically right on time, but we didn't introduce any new material in the week that you guys were taking the exam because that was the week where everyone was shifting to the online sphere, which is where we are now. Because the new material got bumped back by 1 week, I don't feel confident giving you guys an exam with such little new material. So we're also going to be bumping the exam back by a week as a result. So the nature of that exam, I haven't quite figured out if I want it to be the exact same as exam 3 or not. Either way, I'll be letting you guys know via Blackboard in the announcement section. But for now, I'm just letting you guys know that no, we are not taking an exam next week. It is getting pushed back. Same with lab. There were some complications with me being able to go to campus because of the nature of the current stay home, stay safe lockdown in Michigan. I was able to get to campus though yesterday. That doesn't really mean anything to you guys since this is an asynchronous lecture, but new lab stuff is going to be coming soon since I was able to get to campus finally. So lab will be continuing. It's just, also kind of delayed a little bit. And I'll be letting you guys know specific expectations once I'm able to get all of that information together. Once I get my lectures edited. I'm rambling now. I'm just gonna let you guys go, okay? Class dismissed.